Benedikt is a professor at the Stuttgart Center for Simulation Science at the University of Stuttgart. And well, as Cameron has already mentioned in his talk, he's the developer of the Unfold toolbox, so make sure to check that out. Benedikt will talk about analysis of EEG event durations. So take it away, Benedikt.
Can you hear me? Can you hear me? Can you see me?
Yes, we can hear, we can see everything.
Perfect. I was a bit worried because there were some hiccups. Okay, yeah, so this talk is going to be perfect in this session because Cameron did all the hard work explaining the methods. I will talk about very similar topic. And this works. Yes, okay, cool. I will start with a very basic task. This is the oddball or P300 task. It works like this. You see letters A, B, C, D. And some of the letters are targets, like the C in this block. So you have to press the right button. And if you see a distractor, for instance, like the B here, then you would need to press the left button. And what we typically see in this kind of experiments is a result like this. So here's time. Here would be a microvolt of the average event-related response. And we see that we get this P300 effect, which is the target has an increased activity here. So in this talk, I want to raise 2 points, and maybe they are related, and maybe they are potential confounds. And the one is that the event duration, so the duration in some sense from the stimulus onset until we press a button, is different between two conditions. So first of all, it varies, as you can see here, reaction time varies, and also it's different between distractor and target. And this, this can directly, similar to what Cameron was talking before, can influence how the shape of our response looks like. And the second potential confound is because we are actually recording overlapping potential. So what we mean with this is that we could have isolated response to stimulus and isolated response to a button press, but we are actually recording both of them together. Now, because we have different reaction times between conditions, these different conditions might have different distances and so also have different overlap in our overlapping EEG. Okay, so what we did was, what I did was run some simulations, and later I will also show you applied to a data set. And in the simulations, I give you an example now with this response shape. So you have a positive peak, and then you have how the ERP looks like depends on the event duration. And I have it's a larger design, but I have conditions with and without overlap. And in the condition with overlap, if I have a response like this, the next response would also occur already during the first response. So we have an overlap here at the end of the responses. And for this one, we would have another overlap here. And then, yeah, you can, this is obviously what we're measuring, and we're trying to exactly using the Unfold toolbox and the approach that Cameron already introduced. We try to recover basically this shape, and we have various ways that we can do this, and we will see which ones might work better than others. Okay. So if in the left corner, I have this no overlap symbol, then there's no overlap in the simulation. If in the right corner, I have the no overlap, I also don't model any overlap. So this right now is basically a very standard analysis or that I could do. So this is again the simulation kernel. I try to recover this. I'm using the Unfold toolbox, which you should really check out. It's awesome. It makes such analysis very easy. And if you're familiar with the Wilkinson notation or this R formula syntax, then you can see that here I'm modeling now this EEG. I'm modeling by an intercept that would be the normal event-related potential, but also by a linear effective duration. And if I understood correctly, this is also what Cameron did in his simulation. Right? If I do this, then I get something like something out like this. So what we can directly see here in the condition where there's no overlap and there's no noise, that we cannot really recover this kind of shape from our simulation. What we can also do is instead of taking a linear effect, we can take a nonlinear effect. So that means that we allow that we are not fitting a single line per time point, but we can also fit more complex shapes. And if we allow to do this, then with some artifacts here or here, we can recover the shape. So now let's have a look what happens if we add some overlap, but we're not actually modeling the overlap. Again, the linear effect doesn't look super good, maybe similar than before. Now we have a little bit more noise added. And if we do the spline effect, but we are not actually modeling the overlap, then, well, we get something that looks artsy, I would maybe say. I don't know, not very good. So it's clear that we also have to model the overlap. And if we do this, then the linear effect still does not recover our simulation here, but the spline effect can actually recover this. Now, this is just one simulation kernel, and I don't want to show you all the images, obviously, so we take some procedure or some accuracy score, and in this case, for each of these curves, we just calculate the mean squared error between this yellow curve here and the yellow curve here, or the yellow curve here, and we get a kind of score. These scores differ between the shapes, so I normalize this. Sorry, here's the mean squared error to the ground truth. 0 would be perfect reconstruction. 1 would be, yeah, what's 1? 1 is if I would just have one shape, so just a normal event-related potential without any event duration information. Okay, so this is the shape we saw before. I have other shapes, something like this, a boxcar, and maybe a half dropping off shape here. If we add the linear effect, then we can see we are much better, typically, except in the boxcar, we are better than just fitting a fixed constant. But if we add the spline, then we are, well, we can pretty much recover any shape to some extent. So there will always be some error, even though there's no noise in the simulation yet. I don't have time to really go into the noise, but I want to show another thing that you could do. And that is, you could, instead of fitting it as a duration or so, you could categorize the event durations into, let's say, 8 bins or something like this, and then try to recover the shape for each of the bins. And this is something like this, and I was a bit surprised that it looks that it's so flat. But okay, the thing is that this is still better than assuming the linearity, but it's also a little bit over optimistic because we are actually checking where the bin center is exactly where we are also checking the mean squared error. Okay, I want to show you also how this could look on real data. So I'm making use of exactly this experiment in the ERP core dataset. And that dataset has 36 subjects that I could use, 200 trials only. So in total, 200 trials. So it's not that many. I generally don't use baseline correction. And this average reference. Okay, so I showed you this before, this rector target, that's a very typical effect. And yeah, please, these are preliminary results. As Christoph said, I'm setting up my own lab, and well, it's challenging to find time for research. Okay, I'm assuming that there's overlap of the potentials in the EEG. For now, I'm not modeling the overlap, and let's see what comes out. This is my formula, so I model trial type and RT. I also model the button press, but it is not shown here. That may be a distraction only. I only show one condition because else it would be too messy. I show the condition effects later. Okay, this is normal ERP if you just run an ERP. This would be with a linear effective reaction time. So we definitely see that there is something to be explained by reaction time. And this would be the same effect just with splines. And as you can see, there's qualitatively, there's some similarities maybe here. Maybe it's a bit stronger or not. I don't want to go too much in the details. I also not sure how much I trust all of this to interpreting small details. But now I want to see what happens if I also model the overlap. So I get a shape that looks quite similar to what I had before. The reaction time is now effect is now, well, much reduced, I would say. But I get vastly different results if I allow the reaction time effect to not be linear, right? So then I uncover again. I uncover actually, I would say, 2 reaction time effects. One maybe at 400 milliseconds and one even late, going probably into the period where the button press definitely are. Okay, and now I promised that I also look at the conditioned effects. So this is again what we saw before. This is distractor, this is target, this is the typical ERP that you would get. That's what everybody's been doing in some sense. If I now add the overlap correction, then I get an ERP that looks quite similar, I would say. Maybe the effect even starts a little bit earlier, but okay. This is not, yeah, I would argue this is not the things that we should look at, but we should probably look at what will be coming up here. And now the interesting bit is if I control for RT, so I model the reaction time, and now I can look at what would happen if distractors and targets would have had the same reaction time, right? What kind of potentials would I get? And then, as you can see here, for the stimulus-related response, there's not much effect left anymore. And yeah, there's I don't show it here, but there is still an effect of target and distractor on time locked to the button press, but it's not time locked in this case to the stimulus onset. Well, okay, preliminary results, we have to do many checks. Where are the statistics? This is not statistically tested yet. I want to test it on other data sets and see how it generalizes. And just, yeah, well, I will first thank my new institution for giving me the possibility to set up a lab. I want to thank all the contributors of the Unfold Toolbox and for this project, especially Olaf Diemigen, Annalisa Gerd, Philip Allday for their constructive discussions along the way. And the take-home messages are, well, 1, you should probably model your event durations. 2, you should probably model them non-linearly and not linearly, but it depends on shape. And 3, you can model event durations and overlap both at the same time, which is great news, I think, for us. Yeah, thanks. I'm happy to take questions.
Thank you very much, Benedikt. Maybe one question from myself. So you showed that, well, modeling, well, especially the nonlinear modeling improved your outcomes, but when you do the nonlinear modeling, you add another parameter or parameters. How do you find a good or the best parameter? And how do you know what's a good parameter if you don't know the ground truth?
Yeah, that's a very good question. A question that is there are multiple answers to. Right now, we're working on automatic methods to do so. The point is that if you get very flexible, if you allow very flexible regression splines, then you would also run into overfit. And you can do cross validation in the Unfold Toolbox to try to find this number, but it's not. Yeah, it's just a challenging problem with this kind of large regression problems to do it automatically in a regularized way or something like this. But that would be options that you have. Yeah.
Okay, we have more questions. So Emcee Zainab asks, well, first of all, thank you. It was very interesting. And I wonder if you can differentiate longer overlapping activations such as gate and ignition.
Yeah, this is it's a very interesting question. We have a data set, but we haven't looked at it yet for gate. Because gate has this time locked that maybe go over seconds or so activity, I think you can subtract it in some sense. There are also ICA-based methods that try to subtract the gate method. Maybe they are also suitable. I don't know.
Okay, and another question from David Ricardo Quiroga Martinez. Does that potentially mean that P3 effects are mostly related to behavioral responses and reaction time rather than purely cognitive processes?
Well, probably not, I would say. I don't know. There are papers on P3 that show that P3 is partially stimulus locked and partially reaction time locked. And so maybe the stimulus locked version of the P3 is just in some sense a consequence of the different reaction times and different overlapping potentials. Maybe yeah, it's hard to say at this stage, but yeah, it's a possibility. That's something that I'm raising here. Yeah, we will see. Probably it's both, as always.
Okay, thank you very much, Benedikt. And well, thanks again to all the speakers, Cameron, Priyanka, and Benedikt. Thanks to the audience for the very nice questions. And also thank you to Alexandra, who was running the back end and make sure everything went smoothly. Yes, enjoy the rest of your conference, everyone, and goodbye.